Finally, let's take a look at the most complicated coordinate system, spherical coordinates. These coordinates are helpful for describing things like spheres, particularly spheres that are centered at the origin. And our coordinates will include three different components. The first component we call rho, and rho is the distance from your point to the origin. And we typically restrict rho to being positive values. I'll define this first, and then we'll draw a picture second to further illustrate it. Theta is the angle from the x-axis and the xy plane. So really theta is the same type of theta that you were thinking of when you looked at polar coordinates. Finally, the final angle here is the angle phi. Some people pronounce it phi. I pronounce it phi. And this angle is called the angle of declination, and it's the angle that's made with the z-axis. So let's take a look about what each of these pieces mean. So let's say I have a point in R3 represented by P here, and it's going to have three different components. Rho, which is the distance from this point to the origin. So if I were to draw a line, it would measure the length of this line. I'll call this rho. The next coordinate is the coordinate theta. Theta is the angle that's made between the x-axis and the projection of this point down into the xy plane. This is one of the harder ones to visualize. But if I were to take this point in space and project it down into the xy plane, theta measures out the angle that's swept out from the x-axis to this projection. And then finally, the final angle is the angle phi, the angle of declination. And the angle phi is the angle that's made up here with the z-axis. I think that in some ways that's the easiest point to be able to visualize. So this is my z-axis. So how do we go back and forth between rectangular coordinates and polar coordinates? How can I express this point in terms of x, y's, and z's? We're going to use triangle geometry again. So the first thing that I'm going to do, I'll go ahead and write on here, and hopefully you'll be able to see the pictures that I'm making. So this is this point. Let's say that I were to make a right triangle from this point to the z-axis. Notice that this may look a little funny to you, but it's because this wedge of a triangle has been spun outwards, and that's why it looks like it's sort of squished. It's not actually squished, it's that this point is coming up towards you, and that's why you're viewing it the way that you do. And I want to know, what's this height z? So if I abstract this a little less, the angle that's made with the z-axis here, this is this right triangle, where my angle phi is the angle made with the z-axis. This is the z-axis, and this is my point P. I've just reoriented this triangle to see it a little better. We see that this is just a right triangle, and that the length of this side, we know what the hypotenuse of the triangle is. The hypotenuse is given by our rho value, which is sort of our distance from the point to the origin. It's exactly the distance from the point to the origin. And it means that this angle, or this side length, can be given by the cosine of phi, because the cosine of phi is going to be adjacent over hypotenuse, or in other words, this height z I'm thinking of z naught. Let's call that z naught is the z coordinate of this point. So in this case, z naught is going to be equal to rho times the cosine of phi by that triangle geometry. So we've solved one of our points. Let's look at the other points. In order to look at those points, we're going to have to focus on what's going down in the xy plane. I want to know the distance in the x direction, and I also want to know the distance in the y direction. So let's look at the projection down into the xy plane. This length here is rho, and this length is the projection of rho down into the xy plane, which also forms a right triangle. It's this right triangle here, because this is a straight line going straight up, and this is a line that lives down in the xy plane. And I'm going to draw this triangle over here. That's the easiest way. This is the way I'm going to visualize this triangle. So again, we're thinking of rho as this side length. We're thinking of this height here as our z height that we just found, z naught. And we know that this angle right here is phi, which means that by alternate interior angles being equal, this is also phi. This length right here is the cosine, or is rho times the cosine of phi, and this along the bottom is going to be rho times the sine of phi. I recommend that you draw out this triangle yourself to better visualize it. But it means that the projection down here is rho times the sine of phi. This length right here is the same length as the length along the top up here of this triangle, because these two triangles sort of meet together to have this side length of rho. But we're almost done, because now we can just distill this down into a top view into the xy plane. I'm shifting the orientation a little bit, but down in the xy plane, whoops, I can't see that very well. We see that we have our angle theta is the angle that's made with the x-axis. We see that this projection length is the length rho sine of phi. And so that way, to figure out our x and y coordinates, we can also use triangle geometry and see that, aha, this length is going to be, it's like the cosine of theta, but I have to multiply it by the hypotenuse length, which is rho sine phi, meaning that my x coordinate becomes rho sine phi times the cosine of theta. And my y coordinate becomes y equals rho sine phi, because that's the hypotenuse here, times the sine of theta, because the height of this triangle is the sine of theta. Let's summarize. Oh, I have these boxes all over the place. It means that for my point, given in polar coordinates, my translation into x, y, and z coordinates is going to be given by my x coordinate is equal to rho sine phi times the cosine of theta. My y coordinate is going to be given by rho sine phi times the sine of theta. And the z coordinate is just going to be rho cosine of phi. Now this is something that you can memorize, but for solving these problems, you're going to have to think through the elements of the geometry. So it's not enough to just memorize it. I also do need you to use some trigonometry to be able to think through where these points are located on space. Where these points are located in space. One of the things that I tried to do here is to write in green the piece that's hard to remember. That the reason why we have this extra coefficient is because this green piece is the projection of P down into the xy plane. It's the length of this green side length, which is the base of that triangle down there. And that's why it's not just straight cosine of theta and sine of theta like it was in polar coordinates. So now that we've describe what this coordinate system looks like, let's do an example. So, for example, let's say that we have a function given by rho equals 3, theta goes from 0 to 2 pi, and phi goes from 0 to pi. Let's remember what each of these pieces mean as we draw this picture. Rho is the distance from a point to the origin, so we're holding the distance from these points to the origin constant at rho. Theta is the angle that we sweep out with the x-axis, telling us that we need to sweep out a full circle in the xy plane. So let's go ahead and add that information to our graph. We need rho to maintain a constant distance 3 from the origin. Our theta value tells us that we're making a circle that's a perfect circle in the xy plane, obviously. What is this phi angle telling us? The phi angle of 0 is when a point is making an angle of 0 with the z-axis, and as phi increases, that's swinging outwards at increasing angles. And phi is only going to swing out until we get to pi. So this is pi over 2 because I'm making a 90-degree angle with the z-axis, or a pi over 2-degree angle. And I'm going to swing all the way down until I'm making an angle of pi, I guess, with the positive z-axis. So it looks like this might just be a half circle, right? Because my phi angle is only going from here down to here. But because my phi angle and my theta angle work together simultaneously, taking this arc and spinning it in a full circle in the xy plane, if you could imagine this as like maybe a folding fan, or even one of those cool lamps where I'm going to unwrap the lamp in a full circle in the xy plane, that means that this is actually going to trace out the entire sphere. The phi angle is taking care of this arc, and the theta angle is tracing it around in a full circle. If the phi angle had gone in a full circle, notice that we would be actually double counting, because I would be filling out this entire circle and then spinning it not just once, but twice around. Each edge would go an entire way around, and that would be too much of a circle. So this is why we call it spherical coordinates, because this is a simple way to be able to describe a sphere of radius 3 in 3 space.